Okay, so let's just talk about the chapter of heat transfer. So before that, we need to know what is actually the meaning for heat transfer. Okay, so heat transfer is actually defined as the transference of heat energy from one point to another. So this is the meaning for heat transfer. And heat transfer can occur in three ways. So heat can be transferred in three ways. This in three ways. So the three ways consist of solids, liquid, gas. So this is the three ways for the conduction of heat, and this is the definition for heat transfer. Alright, so at first we are going to discuss about the heat conduction. Heat conduction through solids. Solids. Okay, so heat conduction through solids consists of two ways. So for the first way is actually the vibration of lattice atoms. And this is the first way. And for the second way is the collision of free moving electrons. So this is the second way. And okay, so let's just begin with the vibration of lattice atoms. Okay, so this is, let me just erase this one. Alright, so let's say I have a metal, not metal, the object. So this is my object, and this is the point A and the end of the object, which is point A and B. And let's say I supply my heat to this object, and the heat supply is actually start from point A. And let's say this will be my lattice atoms of this object. Okay, so let's say this is the heat. And for the first one, when heat is supplied, so the energy of the first column of this lattice atom will increase. So increase in the energy of the first column of lattice atoms will causes it to vibrate. So this is the vibration of lattice atoms. So I can say that for the first statement, when heat is supplied to one end of the object, so the lattice atoms will begin to vibrate. So this is the keywords: vibrate vigorously with larger amplitudes. So basically we can see that when the heat energy is transferred to the lattice atoms, so the first column of these lattice atoms will begins to vibrate from left to right and left to the left to the right to the left and to the right. So this is the vibration of lattice atoms. So after the vibration of the first column, so we can observe that it will eventually collide with the second column of the atoms. So this second column of the lattice atom will eventually start to vibrate. So this will be vibrate, and this same goes to the third column. And they will start to vibrate, and the third column of the lattice atom will collide with the following lattice atoms. So for the second statement, vibration of lattice atoms causes them to collide with the neighboring atoms. So this is for the second statement. Alright, so after the vibration, so it will eventually collide with the neighboring atoms. So for the third statement, so when the collision occur, I can conclude that the heat energy is actually being transferred from here to here. So I repeat again, collision between the lattice atoms causes the heat energy to be transferred, and hence I can conclude that the heat conduction is actually occur. Okay, so okay. Um, so collision of the lattice atoms causes the heat energy to be transferred. So this is um, the explanation for the third statement. So I can conclude that the heat conduction is actually occur. So this is how we explain the mechanism of heat conduction through lattice vibration, and this is the first one. Okay, so let's just move on to the second way of the heat conduction, which is the collision of free moving electrons. Okay, so this is the heat conduction through collision of free electrons. So this way is actually, for me, is quite similar for the ways that lattice vibration did. And for the first statement, so let's say this is my metal rod, and to be note that the free and this is free moving, and the free moving electron is actually only exists in metals and semimetals. So insulator which is not non-metals has negligible free moving electrons. So this semi-metal, as a note, the temperature of the surrounding should be higher, and we will discuss this one in the next coming parts. And let's just discuss the mechanism of heat conduction through collision of free electron first. And let's say I have my electron in this metals. Okay, so this is the electron, and all of them, I can say that it's actually move in the constant speeds, and move in the constant speeds. And when the heat is supplied to these electrons, so when eventually the kinetic energy of this electron is eventually will increase. So increase in kinetic energy causes the speeds of this electron to be increased. So okay, so for the first statement, when heat is supplied to one end of the metal, so the kinetic energy gained by the electrons will increase. So this is the first statement. As for the second statement, so the increase in kinetic energy causes the speed of this electron will be increased. So the increase in kinetic energy will causes the electron will collide with the other electrons. So this will collide with this one, and this one will be collide with the third electrons, and third electron will collide with the fourth electrons, and so on. So increase, so let me just observe. So increase in kinetic energy. So this one should be free moving electron. So this, we must state this one specifically. An increase in kinetic energy of free moving electrons, of course, causes them to collide with each other. So increase in kinetic energy of free moving electrons causes them to collide with each other. So collision of electrons, and this is the third statement, and collision of free moving electrons causes the heat energy to be transferred. And heat energy transference in heat energy causes the heat conduction to be occur. And this is my conclusion, which is collision between free moving electrons causes the heat energy to be transferred, and hence the heat conduction occur. So this is the mechanism of heat conduction through collision of free moving electrons. Just like so. Okay, so we have done for both mechanisms. So let's just move on to the next parts. Okay, so let me just erase this one. And this one as well. Okay, so let's just talk about the difference. Okay, this is the difference. Difference between metals, and this one should be the additional parts. Metals, semi-metals, and insulators. So we mentioned just now, metals consist of free moving electrons, and this one is the semi-metals is consists of free moving electrons if the surrounding temperature is higher, and insulator has negligible free moving electrons. So let me just list out all. So metals can conduct heat to the lattice vibration, and collision of free moving electrons. So as for the semi-metals, so this is the semi-metals also consist of lattice vibration as well. So as for the collision of free moving electrons, so the temperature required is actually much more higher than the normal temperature. As for the insulators, so insulators consist only the lattice vibration. So why this is this so? And we will discuss it now. And okay, so let me just erase all this one. Okay, this one as well. Alright, so let's just start with the metals. So we have two bands, which is valence band and conduction bands. Conduction band. So initially, when heat is not supplied, the electron is actually inside the valence band. So this is okay, so let me just draw it out. So when heat is supplied, the energy gained by the electrons increase. So valence band is actually meant by the electron is actually inside the electron shell. So when heat is supplied, so the heat energy is supplied, so this electron is actually get excited and move from the lower energy level to higher energy level, and how should I describe this one, and eventually out from the electron shell and become the free moving electrons. So for this process, so let me just write it in terms of keywords. So this process is only need small amount of small amount of energy. So if the small amount of energy is supplied to this metal, so the electron will eventually get excited and jump from this valence band to conduction band. Okay, so as for the insulators, so this is the conduction band, and this one should be the insulator, of course. So this is the valence band. So valence band, as I mentioned just now, is actually in the electron shell. So as for the insulators, how should I say? As we learn from chemistry, and um, wait, so not chemistry theory. It should be the basic theory. So this is the gap. So okay. So we can see that this is actually there is a gap between the valence band in and conduction band in the insulator. So this large gap causes a barrier for electron to jump from valence band to conduction band. Okay, so in this case, so in this case, we can say that large amount of energy is okay is required. So large amount of energy to enable the electrons to jump from valence band to conduction band. So this is how we said that. This is why we said that the insulator actually has a negligible electrons, since the electron is quite difficult to jump from valence band to conduction band. Okay, so as for the semi-metals, of course, semi-metals, and I believe this one should have a dash here. So this is semi-metals. And this one, so we have a gap here, and this is conduction band, and this is valence band. So when heat is supplied, the electron is able to jump from valence band to conduction band to be the free moving electrons in order to conduct heat. And okay, so in this case, higher energy means the energy which is higher than the energy needed for the metal. Okay, so higher energy is required. So if the energy is higher than expected, is higher than the energy which required for the metals, so the electron will eventually jump from valence band to conduction band. So this is why I said that the temperature for semi-metal should be higher. So this is the reason. And insulators has the negligible free moving electrons, since the electron is quite hard to jump from valence band to conduction band. Alright, so this is the reasons. Okay, so let's just move on to the next part. Okay, and this one, let me just erase all this one. Alright, so let's just move on to the new topics, which is thermal conductivity. So, thermal conductivity. So before that, we need to know some basic principle. And let's say I have my object A, and this will be my object B. And let's say this object A has a temperature which is 100 degrees Celsius, and this we have 50 degrees Celsius. So the heat is actually eventually will move from higher temperature region to lower temperature region. So this heat will eventually move from A to B, which is the both object is actually keep contact, or which we can say that the two object is actually keep in touch, and the heat will eventually move from part A to part B, and the heat will move from part A and to part B to part A, back and forth until these both objects achieve thermal equilibrium. So what is actually meant by thermal equilibrium? So thermal equilibrium is actually meant by same temperature achieved by both objects. So when these two objects actually achieve the thermal equilibrium, so the temperature for them is actually the same. So let's say this is 50 degrees Celsius and this one as well as 50 degrees Celsius. So this is thermal equilibrium. And okay, so we've done for the basic principle. So let's just enter for this subtopic, thermal conductivity. And let's say I have my wire here, and this is my wire, and this is my A, and this is my change in and this is my distance. So my distance, I denote this one as delta x. So this is my part B. And okay, so let me just write this one down here. Okay, so I just change the point. So let's say this is my point P and this is my point Q, and this A, we denote this one as the cross-sectional area of the wire, which is assumed to be pi r square. So when I supply my heat from point A and from point P, so this heat is actually basically will move from here to will move from point P to point Q. And why is this so? This is because when heat is supplied from point A, so point A eventually have a temperature which is denoted as theta. So this theta is actually much more higher than the temperature of other points, and because the heat supply is started at point A. Okay, so in order to achieve thermal equilibrium, so the heat will actually move from point P to point Q. And as for the temperature at point Q, so I can say that the temperature at point Q, which is denoted as theta prime. So this theta prime is actually the lowest temperature at all points. So this because the heat approach, how should I describe this one? So because of the Q has the lowest temperature, because it is the last point where the heat came from, which is from point P to point Q. So this point P, this temperature at point P and this temperature at point Q, so I can conclude that my theta prime from here is actually equals to the initial temperature minus the change in temperature, which is along the point from point P to point Q. Okay, so from this graph, okay, let me inscribe this one in terms of graph. Okay, so this is my graph. Oops. And this one shall be my graph. Alright, so this is my temperature, so, or should I say T, and this is my X, and so this is my, okay, so this one is degrees Celsius, of course, and let's say this is my theta, where the point A located, and as we said that the temperature is actually decreasing because the point A has the highest temperature, which the heat supply start from. Okay. So since the heat supply start from point A, so it means that the point, not point A, sorry. It means that the point P has the highest temperature. So I assume that the point P is actually start from 0. So, okay, so the temperature is actually decreasing until one point. So this is the point where this is the temperature where point Q located. So this is theta prime and this is point Q, and this one should be point P, sorry. Okay, so why the temperature will not touch the x-axis? This is because the experiment is actually conducted in room temperature. So room temperature is impossible for the wire to reach the 0 degrees Celsius if the experiment is conducted at room temperature. So this is the point where this is the temperature where Q located. Alright, so we can observe that the distance and the temperature is actually forming a straight line. So we know that straight line is actually have a how should I say, has a main component which is gradient, which is denoted as m. So we know that gradient is actually equals to y2 minus y1 divided by x2 minus x1. So, okay, let me just write it here. So what will be my y2 here? So my y2 is actually theta prime minus theta. So my x, this one will be my delta x, and my x2 is actually delta x minus the initial distance, which is 0. So theta prime is actually equals to theta minus change in theta. So change in theta is the temperature along the point from P to Q. And this is theta, and this is change in x. So what we get finally is actually the change in theta, which is from point P to point Q, divided by the change in x. So delta is actually equals to delta d theta over dx. So this is what we call temperature gradient. Alright, so this is the first component that we need for the formula of thermal conductivity. Okay. So it is found that my rate of heat flow, so rate of heat flow is actually the how should I describe this one, as the speed of heat flow from point P to point Q in the wire is actually directly proportional to the cross-sectional area of the wire. So the cross-sectional area of the wire is high and the rate of heat flow is very faster, and this one high and this one will high. And if the cross-sectional area is lower, and this causes the resistance of the wire to be increased, and hence the rate of heat flow will also be slower. Okay, so this is the first information. And for the second information, so if the okay, so for the second information, the rate of heat flow is also directly proportional to the temperature gradient. So if the temperature gradient is high, it means that the rate of heat flow is also high. This is because the heat flow is about to move from hotter region to colder region, and this negative sign is actually indicates the direction of heat flow in decreasing temperature. So if the temperature gradient is higher and the rate of heat flow is higher. Okay, so from these two information, we can combine it into one relation. So dq over dt is actually directly proportional to negative a d theta over dx. So this is the relation. And in terms of equation, so my dq over dt is actually equals to negative k a d theta over dx. So this is the formula for the rate of heat flow. Okay, so let me just erase all this one. Okay. So I still need this formula and dt. So from here, I can there's a constant which is k. So this k is actually shows the thermal conductivity of different materials. So if the this K shows the thermal conductivity of different materials. So if copper has its own thermal conductivity and silicon has its own thermal conductivity, Okay, so from this equation, I can derive this thermal conductivity. So is equal, K is actually equals to negative dq over dt divided by the A d theta over dx. Okay, so let me just erase all this one. So from here, uh, I get from this formula, what I get is the definition for thermal conductivity, which is defined as the rate of heat flow per unit cross-sectional area per unit temperature gradient. So this is the definition for thermal conductivity. Okay, so from this relation, I can observe that. So let's say if the thermal conductivity is smaller, not thermal conductivity, sorry. So let me just erase this one. So okay, so if the temperature gradient is slower, so I can say that my thermal conductivity is higher. So let's say I have my wire. So the heat supply is actually start here. So if what I get is the 100 degrees Celsius, and this finally is actually the okay. So this one should be 90 degrees Celsius. So from here I can say that the temperature gradient is slower. This is because the difference is the difference in temperature is very small. So the difference in temperature is very small. It means that the heat is transferred from point A to point B. So the heat transferred from point A to B is very fast. So the heat transfer from A to B is very fast. So I can conclude that my temperature gradient is smaller. So if we represent this one in graph, so what I get is actually the straight line which is less steeper. So the less steeper graph is shows that the temperature gradient is smaller. So the smaller the temperature gradient, the higher the thermal conductivity. So I can conclude that my conductor, so this conductor is actually a good heat conductor. Okay, so this is the relation. So conversely, if the temperature gradient is higher, so it means that the thermal conductivity is slower. It means that the heat flow is actually take very long time. So since the heat flow is very long, so the time since the time taken for the heat flow is very long, so it means that um, the thermal conductivity of this wire is very low. So I can conclude that this wire is actually not a good heat conductor. So this is how we determine the relation between thermal conductivity and the temperature gradient. Okay, so we have done for thermal conductivity. So let's just move on to the another parts. So let me just erase all this one. Okay. So let us just continue about the thermal. Okay, so let me change the color. So thermal conduction in perfectly insulated road. So let's just give you a moment. Okay. So let's say I have a wire. Okay. This is a wire. So the outer layer of this wire is um actually surrounded by the insulator. So this is my wire, or I can say this is a rod, and this is the insulator which is wrapping the rod insulator. So the purpose of wrapping the rod with the insulator is to prevent the heat lost to the surroundings. So this is why we okay. So this is why we wrap the rod with insulator. Okay, so since there is no heat loss, the temperature at every point of this rod is actually equals to, okay, so let me just write it down. So since, okay, just give me a moment here. Okay, so since no heat loss, so I can conclude that the temperature gradient so my temperature gradient is equal to 0. So why my temperature gradient is 0? This is because when this rod has the temperature which is at any point is actually all the same. So let me just write it down. Temperature at every point are the same. So if the temperature at every point are the same, so it means that no heat flow in this rod, and hence the temperature gradient is equal to 0, since there is no difference in temperature at every point. Okay, so this is the thermal conduction in perfectly insulated rod. Okay, so let us just move on to the another parts. Okay. So this part is actually still the same subtopic, which is the thermal conduction in perfectly insulated roads. Okay, so we are still discussed in this perfectly insulated road. Alright, so this is the insulator which wrapping the roads. Okay, and this is the another end of the roads, and this is the roads. And what if I place this rod keep contact with another two objects? So let's say this is my object A and this will be my object B. And we know that this two object is actually has the different temperature, and I denote this one as theta 1 and this one is theta 2. And these two object is actually keep in touch to each other. So okay, so let's say this is my theta 1, and let's say I supply my heat to here, and this is theta 1, and theta 1 has the higher temperature than other points in this road and the object B. So this will be my theta 2, which is the temperature for object B. So initially, for the first second and the second seconds and the third seconds, the temperature is actually varying, and this I consider this one as the first seconds, and this is the second seconds, and this is T2, and this is T3. So we can see that from time 1, time 2, and time 3, the temperature, due to the different temperature at every point, the temperature is actually varying. So the varying due to the heat flowing from A to the road and road to the B and B to the road and road to the A. So until okay, so this is how this is the reason why the curve is still varying. So let me just uh, draw it more properly. So okay, let me just draw it in different color. So let's say this is my first seconds. So this is my first seconds, and this will be my seconds, which is T2, and this is my third seconds. So due to different temperature at every point, so due to the temperature at every point, so the curve is actually varying at all points. So and this is T1, T2, and finally T3. So finally at time t, which is capital letter T, so it will eventually vary with a steady state. So let me just okay. So at one time, which is time t, so the temperature will actually varying at the constant state, which is we call this one as steady states. Okay, so at time t, the temperature gradient at all points are actually constant with time. So T1, at T1 the difference in temperature at all points is actually quite different. and this same goes for T2, and this same goes for T3. As for the time T, which is capital letter T, so the difference in temperature, so at all point is actually constant, and this will give us a straight line for temperature gradient. Okay, so hence I can conclude that the rate of heat flow is actually constant at every point. So at steady states, when the these three objects achieve the steady states, so I can say that the rate of heat flow is actually all the same, are the same at every point, from point A to the road and road to point B. And at the initial states, for T1, T2, T3. So since the difference in temperature at every point are not the same, so let's say this is my theta 1 at point A and this is the theta prime. So the difference in temperature between object A and the roads, and this is the road, is actually not equal for the difference in temperature between the road and the object B. So not different in temperature. So this will not give us a straight line for the temperature gradient. And this is theta and this is distance. So as when the steady state is achieved, which is time t, and I can say that the difference in temperature for object A and the road is actually equals to the the difference in temperature between the temperature of the roads and the temperature of the object B. So this is theta 2 and this is equal. And this one, and the rate of heat flow for T1, T2 and T3 is actually not constant. As for the steady state, the rate of heat flow at every point is actually constant. So I can conclude that, okay, let me just erase all this one. Okay, so I can conclude that, so this is my x, and which is the distance from A to B. So this is my dq over dt. So this is actually in the steady states. So the dq over dt is actually constant at every point. So this is the how we define the rate of heat flow for the perfectly insulated roads at the steady states. So if when steady state is achieved, so the formula for the rate of heat flow is actually applicable. So dq over dt is actually equals to the ka d theta over dx. So okay, so just now we mentioned about at steady state we mentioned about the road. Okay, so let me draw again that roads. So this is A and this is the roads. So this road is perfectly insulated, of course. So this is B. And we discussed about this is the theta 1 and this is theta prime and this is theta 2. And we said that at steady state, theta 1 is actually, the difference between theta 1 is actually equals to theta prime is equal to theta prime is difference in theta prime and theta 2. Okay, so since the rate of heat flow is constant at every point, so let me just highlight this one. Every point, the heat constant, the rate of heat flow at every point are the same. So so the temperature, how should I say, the difference between the difference in temperature, so the difference in temperature for every points are the same. So I can conclude that, so this theta 1 minus theta prime is actually equals to theta 1 minus theta 2. Since the difference in temperature for every point are the same, so theta 1 minus theta 2 is also equals to theta 1 minus theta prime is also equals to the theta prime minus theta 2. Okay, so I can conclude that so this theta 1 minus theta 2 divided by L. So this L is actually the distance between all here. So this is how we derive another formula for the rate of heat flow. So since the difference in temperature in theta 1 in theta 2 is also equals to this differences in temperature, and hence I can just use this formula to calculate the rate of heat flow at every point, since the rate of heat flow is constant for every point. So it's not necessary for us to calculate the rate of heat flow one by one, which is the difference in temperature in A and the rod, and the difference in temperature for the rod and the theta 2. So what we need to do is actually calculate the temperature for between the object A and object B, and finally we will get the value of rate of heat flow. Okay, so I think we will stop here now. So we will discuss the other parts in the next coming video. So I'll see you next time. Thank you. Bye.